Hello everyone. In this lecture, we will study our next point, that is generating functions. But before starting our this generating functions point, let's see remaining two theorems of the recurrence relations. Because in the last lecture we have studied about the recurrence relations, okay, and its different examples. Now in this lecture, first see the two theorems of the recurrence relation and our last point, that is generating functions. Okay, let's see first theorem. Theorem first. Let C and C2 be the real numbers. Suppose that R square minus C1R minus C2 is equal to 0 has the two distinct roots, that are R1 and R2. Then the sequence AN is a solution of the recurrence relation. AN is equal to C1 AN minus 1 plus C2 AN minus 2. But the condition is there if and only if AN is equal to alpha 1 R1 raised to n plus alpha 2 R2 raised to n for n is equal to 0, 1, 2, where alpha 1 and alpha 2 are the constants. Okay, so this is our theorem first about the recurrence relation. What is that? C1, C2 are the real numbers, and there is one equation R square minus C1R minus C2, and that equation has the two distinct roots R1 and R2. Now by using this equation we have to determine that the sequence AN is a solution of this recurrence relation. So this is our recurrence relation, and for this recurrence relation the AN is the solution. But one condition is there, if and only if AN is equal to alpha 1 R1 raised to n, alpha 2 R2 raised to n. If this condition is satisfied, then and then only we can say that AN is a solution of this recurrence relation. Okay, so by using this theorem first, let's see one example. Then you can understand what does this theorem says. The question is here, what is the solution of the recurrence relation AN is equal to AN minus 1 plus 2AN minus 2 with A0 is equal to 2 and A1 is equal to 7. So what are these A0 and A1? These are our initial conditions. So in the question itself it is given. These are the initial conditions A0 and A1. Now to solve this example we are using here theorem first. Okay. So the characteristic equation of the recurrence relation is R square minus R minus 2 is equal to 0. How we can get this equation? So this equation is obtained by using the theorem first. See here, suppose that R square minus C1R minus C2 is equal to 0. So this equation has the two distinct roots R1 and R2, and in this equation C1 and C2 are the two real numbers. So by using this equation we can create our characteristic equation for this recurrence relation. Okay, recurrence relation is given in the question itself. This is so R square. So this AN stands for this R square. Now this left hand side is take this left hand side into the take this right hand side into the left hand side. So by taking this right side into the left side, all the signs are changed. So by taking this AN minus 1, this stands for R. So this is the sign of this R is minus, and this also by taking this into the left side, sign will be changed to minus. So minus 2. After solving this equation R square minus R minus 2, we got the two roots R1 and R2. R1 is 2 and R1 is 2 and R2 is minus 1. Okay, so how we can get this equation? By using the theorem first. Now we can say that the sequence AN is a solution to the recurrence relation. So condition is there. This condition is also given in our theorem first. What is that condition? This is our condition. An is equal to alpha 1 r1 raised to n plus alpha 2 r2 raised to n. Now put the values of r1 and r2 in this equation. So by putting the values, r1 means 2 raised to n, plus r2 is equal to minus 1 raised to n. Okay, for some constants alpha 1 and alpha 2. So up to this point we got the r1 and r2 values. Now obtain the alpha 1 and alpha 2 values. How we can obtain that values? See here. From the initial conditions it follows that. So what are our initial conditions? See here. These are our initial conditions. A0 is equal to 2 and A1 is equal to 7. So use that initial conditions here. An is equal to alpha 1 2 raised to n plus alpha 2 minus 1 raised to n. This equation we obtain by putting the values of r. Okay. Now our first initial condition is A0. A0 is equal to 2 is equal to, we got here alpha 1 plus alpha 2. How we can obtain this alpha 1 plus alpha 2? By putting the value of n is equal to 0. By putting that value n is equal to 0, we got here A0. Then after putting 2 raised to 0, 2 raised to 0 means 1. So we got here the alpha 1 plus alpha 2 minus 1 raised to 0. So remember here minus 1 raised to 0 always plus 1, not minus 1. Okay, please note here minus 1 raised to 0, the result will be plus 1. That's why we obtain the equation here alpha 1 plus alpha 2. Understood? Now similarly A1, the second initial condition is A1 is equal to 7 given in the question. So by putting the value of n is equal to 1, we got here A1 is equal to alpha 1 2 raised to 1. 2 raised to 1 means 2. So 2 alpha 1 plus alpha 2 minus 1 raised to 1. So the result of minus 1 raised to 1 is always minus 1, not plus 1. What about the minus 1 raised to 0? Minus 1 raised to 0 is always plus 1. But minus 1 raised to 1 is always minus 1. That's why the sign of the 1 in this equation is minus. Okay, you understood the difference. Minus 1 raised to 0 is plus 1. Minus 1 raised to 1 is equal to minus 1. So how we can say that this? You can search on the internet also. But this is the mathematical statement. We can't change into that mathematical statement. Okay, this is the mathematical condition or mathematical statement. So we can't change in that statement. So take as it is. Minus 1 raised to 0 is plus 1. Minus 1 raised to n is equal to minus 1. So after solving these two equations, we obtain alpha 1 is equal to 3 and alpha 2 is equal to minus 1. Okay, by putting this, by solving these two equations A0 and A1. Hence, finally or consequently, we can say that the solution to the recurrence relation and the initial conditions is the sequence an with an is equal to alpha 1 2 raised to n plus alpha 2 minus 1 raised to n. Now put this value of alpha 1 and alpha 2 into this equation and we got the final equation, this one. An 3 into 2 raised to n minus 1 raised to n. Okay. This is our example which is based on the theorem first. Now see theorem second. Let C1 and C2 be the real numbers with C2 is not equal to 0. Suppose that r square minus C1r minus C2 is equal to 0 has only one root. This theorem second is also similar like the theorem 1, but difference is here. In the theorem first there are the two roots r1 and r2, but in the theorem second there is only one root is there, r0. Then the equation an is the solution of the recurrence relation an is equal to c1 an minus 1 plus c2 an minus 2. Same the condition is here if and only if an is equal to alpha 1 r0 raised to n plus alpha 2 into n into r0 raised to n for n is equal to 0, 1, 2 up to infinity. Okay, where alpha 1 and alpha 2 are constant. Then by using this theorem second, we see here our next example. The question is here, what is the solution of the recurrence relation an is equal to 6an minus 1 minus 6an minus 2? With the initial conditions are there, a0 is equal to 1 and a1 is equal to 6. Now by using the theorem second, we can solve this problem. First we have to create the characteristic equation for the recurrence relation. How we can create? As I have already told you in our example first. Likewise, same an stands for the r square. Now take this right side into the left side. Now the sign will be changed. Plus sign will be changed to the minus, that is 6r, and this minus sign will be changed to the plus, that is plus 9 is equal to 0. After solving this equation, we got only one root here, that is r is equal to 3. Understood? Next, the sequence an is a solution to the recurrence relation if and only if this condition, means this equation, is satisfied. Now by putting the value of r, we got this equation: alpha 1 3 raised to n plus alpha 2 n into 3 raised to n for some constants alpha 1 and alpha 2. Now using the initial conditions, it follows that we know, or in the question itself, the initial conditions are given: a0 is equal to 1 and a1 is equal to 6. Use these values. a0 is equal to 1. Now put the value of n is equal to 0 into this equation. What is our equation? Put the value of n is equal to 0 by putting the value r0 raised to 3 raised to 0, 3 plus alpha 2 into n, means into 0, means this whole term will be 0, and we got here the alpha 3 alpha 1, or sorry, alpha 1, 3 raised to 0 means 1, so that we got here the only a0 is equal to alpha 1. Next, by putting the value of n is equal to 1 is equal to 6, putting the value of n is equal to 1, a1 3 raised to 1 means 3, and n in 1 into 3 raised to 1 means 3. So we got the equation 3 alpha 1 plus 3 alpha 2. Now solve these two equations and we got the values alpha 1 and alpha 2. Alpha 1 is equal to 1 and same alpha 2 is equal to 1. Now we can say that finally the solution to the recurrence relation and initial conditions is the sequence an with an is equal to alpha 1 3 raised to n plus alpha 2 n into 3 raised to n. Now put the values of alpha 1 and alpha 2 into this equation, and this is our final equation, that is an is equal to 3 raised to n plus n into 3 raised to n. Next, now this is our last point in this unit, third unit. Okay, what is that? The generating functions. The generating functions can be used to solve many types of the counting problems, such as the number of ways to select or the distribute objects of different kinds, subject to a variety of the constraints. Now these generating functions can also be used to solve the recurrence relations by translating a recurrence relation for the terms of a sequence into an equation involving a generating function. Means this generating function can also be used to solve the problems of the recurrence relations. These generating functions are a very helpful tool for studying many properties of the sequences. Next, generating functions are used to represent the sequences efficiently by coding the terms of a sequence as coefficients of the powers of a variable x in a formal power series. In other words, we can say that a generating function is a way of encoding an infinite sequence of the numbers an by treating them as the coefficients of a formal power series. And this formal power series is nothing but our generating function of the sequence. There is an extremely powerful tool in the discrete mathematics which is used to manipulate the sequences, and this is nothing but the generating function. The idea is this: instead of an infinite sequence, for example, suppose there is an infinite sequence 2, 3, 5, 8, 12, infinity. Okay, so we look at the single function which encodes the sequence, but not a function which gives the nth term as output. Okay, not a function which gives the nth term as output. So instead, a function whose power series displays the terms of the sequence. For example, suppose there is a power series is there 2 plus 3x plus 5x square plus 8x cube plus 12x raised to 4, which displays the sequence 2 into 3, 2, 3, 5, 8, 12 as its coefficients. Okay. An infinite power series is simply an infinite sum of the terms of the form Cn x raised to n, and in that Cn is called as a constant. So we can write a power series like this: summation k is equal to 0 to infinity ck x raised to k. So this equation can also be expanded like this way: c0 c1x c2x raised to 2 3 x cube c4 x raised to 4 c5 x raised to 5. So this series is called as a generating series. Now this generating series generates the sequences like this way: c0 c1 c2 c3 c4 c5. Okay, so this is all about the generating function. Means this is just introduction part of the generating function. Now see here the formal definition of the generating function. What is the definition of the generating function? The generating function for the sequence a0, a1 up to ak of the real numbers is the infinite series g of x is equal to a0 plus a1x plus up to ak x raised to k. So this series we can summation means this series we can write this way: summation k is equal to 0 to infinity ak x raised to k. Now this generating function for ak given in the definition, this sometimes called as a ordinary generating function of ak. To why this is called as an ordinary generating function? Because to distinguish it from other types of the generating functions for the sequences. Now this is our the definition of for the generating function, means g of x a0 a1x plus a up to ak x raised to k, and we can write in other words k is equal to 0 to infinity ak x raised to k. So by using this we can solve many types of the generating functions examples. See here one example: determine the generating functions for the sequences ak with. So the ak are given and we have to find out the generating functions for all these sequences. See here, first sequence is ak is equal to 3. So how we can write the generating functions for this? By putting this value into this definition. See here, into this summation is equal to k is equal to 0 to infinity ak x raised to k. Now what is the ak? ak is 3. So put this value into this equation and we got here the generating function k is equal to 0 to infinity 3 into x raised to k. Similarly, next sequence is ak k plus 1. Put this value into this equation and we got here 0 to infinity k plus 1 x raised to k. Same, ak is equal to 2 raised to k. This is the sequence. Now we got here the generating function for 2 raised to k, 2 raised to k into x raised to k. Okay. This is the simple example of the generating functions. We have to determine the generating functions for the sequences. Now see here another example. The question is given here, let m be a positive integer. Let ak is equal to c m comma k for k is equal to 0 to m. Now question is, what is the generating function for the sequences a0 to am? Okay, so understand first question. M is a positive integer. Ak is given, c of m comma m comma k for k is equal to 0 to m. And we have to find out the generating function for the sequence, that is a0 to am. Now, by using the definition of this generating function, g of x, a0, a1 x plus ak x raised to k, we can solve this example. Ak is given. Ak is what? C of m comma k. So by putting this value into this equation, we can solve this example. That is a0, a1 x. So this a0 terms stands for in this example is c of m comma k. Understood? So put this value c of m comma k. But c of m comma k, k stands for 0. So put this value of 0 is equal to into this term m comma 0. Same, c of m comma 1 x plus c of m comma 2 x raised to k up to c of m comma m x raised to m. So finally we got the equation here by using the definition of the generating function. Okay, understood? So by this lecture we have finished our chapter 3rd, which is the combinatorics. Now from the next lecture onwards, means in the next lecture we will start our next lecture. We will start our next chapter, that is unit 4. Okay, thank you.